Good day, class. In this lesson, we will study limits, but this time we will use the limit to define integrals, and as I always like to study, integrals to define limits. Let's take a look. Recall that limits describe a number in which an approximation is approaching. So we're getting closer and closer to something. We described earlier how derivatives, or the derivative of this black curve on the left, can be defined by the slope of a tangent line at a particular point. And we talked about getting closer and closer to that point, coming in from the left or coming in from the right. And this would define a derivative. Regarding integrals, we need to look at this slightly different. In fact, we're taking a look under our curve. We have a red curve here, and underneath that curve, we want to approximate the area, and so we'll be getting closer and closer in a similar fashion as derivatives, but clearly it's going to be distinctly different. Notice how underneath my curve, sketch curve, if you will allow me that, I have three rectangles. So imagine rectangles are measured in some units. So I've measured these rectangles on their two-dimensional measurements, and I've calculated a sum of 1.635. So altogether, this orange space of rectangles is worth 1.635 units of measure, square units of measure. So this is my area, the sum of my areas. However, I see that there's a lot of white space under that curve, and I want to account for that because I'm really trying to describe the area under the curve. And so I'm using integrals to do that. So I'm going to integrate sort of pictorially here. I'm going to increase my number of rectangles, and then I'll measure those rectangles. So I have 7 rectangles here now, and I have some white space under the curve. Again, allow for some graphical misrepresentation here just because I'm just using a limited technology. But imagine 7 rectangles under there, and I've calculated their areas and added them, and I have a sum of areas of 1.7971. So I see my area is getting bigger because I'm closing in on that white space. I'm going to increase my number of rectangles and continue to close in on that white space. Notice what's happening. The sum of my areas is getting bigger. And my white space is diminishing, and I'm getting closer and closer to the true area under that curve. If I could, in a real sense, measure the area under that curve, eliminating all the white space by getting skinnier and skinnier rectangles to infinity, to the point where I close in the white space, I notice here I'm only up to 20 rectangles, but that white space is closing in. I'm at 1.7977 as the sum of my areas. I'm not quite there with all my white space closed in, but I already see the sum of that areas isn't increasing by very much at this point. So I'm expecting a limit at this point. I would continue on to infinity, getting skinnier and skinnier rectangles to the point where I fill in all of the white space. And notice, no matter how large the number of my rectangles gets, my limit is approaching 1.8. I'm never going to get bigger than that. Some of my areas will never get bigger than that. So identifying the limit is going to be very helpful, and this is where this sort of defines integration. Recall that by now you should have been working with limits with respect to derivatives and sort of understanding what that means, and then now transitioning into limits as they relate to integrals and sort of trying to fill in that white space to calculate the area under the curve. This would be the definition of limits, or how limits define integrals and how integrals can define limits.